Hello everyone, I hope you are doing well. This video will concern itself with finding powers of complex numbers in polar form, which will lead us to this rather wonderful thing called de Moivre's theorem. Okay, so let's take a look now, and just to recall from another video or from your practice in our study of trigonometry, that when you are multiplying two polar complex numbers together, you multiply the moduli and add the arguments. Okay, that's our little phrase there, multiply the moduli, add the arguments, keeping in mind that the moduli is r and the arguments are theta. And so if we were going to take a number and raise it to a power, let's say just squaring a number, keep in mind that z squared, of course, just means z times z. So it's like multiplying times itself. So if I let z equal something like 3 times cosine 30 plus I sine 30, okay, then we are remembering to multiply the moduli here means 3 times 3. And adding the arguments means 30 plus 30. So z squared then is simply 9 times cosine 60 plus I sine 60. And I got the 3 times 3 gives me 9, and 30 plus 30 gives me 60. So there I'm done. If I wanted to take another jump up, another higher power like z cubed, all I have to do is that same thing again. 3 times 3 times 3, and 30 plus 30 plus 30. So I get cosine 90 plus I sine 90. So you can see a pattern going on there where I'm just taking the r, the modulus, and raising it to the same power that I'm raising my number to, and I'm taking the angle, theta, and multiplying that times that exponent. Okay? So that if we did something like z to the fifth, well, the modulus is going to be 3 to the fifth power, which is 243, and my angle will be 150 degrees, because 5 times 30 is 150. So there's the pattern going on, and this is what, recognizing this pattern here, is what leads us, and led back a long time ago, this guy named Abraham de Moivre, to de Moivre's theorem. All right? Yeah, that guy lived a long time ago. You should check his life out. It's very interesting. Read a little bio about him. He led a very interesting life. Was kind of friends with Isaac Newton. Anyway, de Moivre's theorem says this, that if z equals some polar complex number, r cosine theta plus I sine theta, then z to the n is just r to the n times cosine of n times theta plus I sine n theta. So, notwithstanding the fact that polar complex numbers are rather odd looking and take some getting used to, this theorem is really pretty simple. All right, we're just raising the modulus to that power and multiplying that exponent times the angle, and that's it. Okay, de Moivre's theorem is really quite easy to use, but of course it has to be. It is using the polar form of a complex number, and it is possible to raise a complex number to a power without using de Moivre's theorem. And I just thought I'd show you that a rather friendly complex number, 2 plus 2i, raised to a fairly low power of 4. We can do this using this rectangular form, using the binomial expansion theorem and Pascal's triangle little shortcuts, which if you happen to know all of that, you can see readily that this will expand to this, what you see right there, all of that stuff. Now, to simplify this, it takes a little bit of work. 2 to the fourth is 16. Then we have those three things right there. 2i times 8 times 4, that gives me 64i. And then now it starts to get a little bit trickier because I squared, of course, is -1. So I have to keep that in mind as I multiply all of that stuff together. And it gives me -96. And then I cubed, you might have forgotten what that is, but that's just -i. So when I multiply all of that stuff together, I just get -64i, and then finally I to the fourth power is +1, so 2i to the fourth power is +16. Now a bunch of like terms there to combine, and the I terms cancel each other out, and I combine my integers together finally to get -64. So we did it. It is definitely possible to raise a complex number to a higher power without using de Moivre's theorem. But as you can see, there's a lot of steps involved, and if that number to begin with was less friendly than it is, and the power was higher, then you can see this would definitely be, as they say in literature, fraught with peril. Lots of places to make a little mistake. Whereas if we took that same number and raised it to the fourth power by first converting it into polar form, okay, and I'm not really going to go into that process here in this video because it was covered in other videos, but 2 plus 2i converted into polar form is 2 root 2 times cosine 45 plus I sine 45. If that is surprising or strange to you, you might want to go back and look at some of the other videos about converting numbers from rectangular to polar form. But now all I have to do is apply de Moivre's theorem to this polar number, raising it to the fourth power, and 2 root 2 to the fourth is 64, and 45 times 4 is 180 degrees, so there's r and there's theta, and I'm ready to go. I can simply write the number just like that, 64 cosine 180 plus I sine 180. And so I have to convert that back into rectangular form, and that's pretty easy, just recognizing that cosine 180 is negative 1, sine 180 is 0, and multiplying 64 times negative 1 is negative 64. I could, if I chose, to write it plus 0i. There is an a plus bi form, complex number, but not really much reason to do that. So that is the process there. I hope you find de Moivre's theorem fairly easy to use, and as you're still getting used to converting back and forth between polar and rectangular forms. Very important kind of foundational skill in this particular part of trigonometry. Okay, enjoy. Bye-bye.